So let's try to link principal value with indented contours. So lemma 4, which is page 340, says that if the function f of z is analytic except for a simple pole at z equals c, and TC is the circular arc that's centered at C, has radius r times e to the I theta, and theta ranges between theta 1 and theta 2, then the limit as r goes to 0 of the integral around the arc of f of z is not going to be 2 pi I times the residue of f at C, but rather I times the difference in the angles. So if you go all the way around, then you get 2 pi. But if you only go part way around, you get the part that's proportional to the angle that you cover, which is actually a really interesting observation, because now this allows us to integrate over the top half, or backwards over the top half, or over any fraction. And all we need to do is take the appropriate fraction of 2 pi I times the residue. In particular, the kind of contour that we're often doing is a contour that comes up to a singularity and goes around in a circle around the singularity and then goes on. So this is the backwards from our normal contour. Normally we do counterclockwise. This is a clockwise contour. And notice that this distance is exactly the same as this distance. So as r goes to 0, this circle is going to shrink to 0, and the distance on either side is going to shrink to 0 symmetrically. So the result that we get is going to be the principal value of whatever integral we wind up getting, because by shrinking symmetrically, we allow a singularity of the type 1 over z minus c. We allow that to actually cancel. So in summary, lemma 4 gives us a powerful tool to integrate partway around a singularity, but the symmetry of where we stop is preserved, because this only works for circular arcs and in the limit as the radius goes to 0. So we're going to come along almost to the singularity, do a little bit of an arc, a little hop around, and then continue on. And in the limit as r goes to 0, we're going to get the right result.